Okay, so welcome everyone to week 8 guided study group of Math 140. So this week is going to be it's midterm 2 exam. So I'm gonna have a quick exam review for midterm 2 of Math 140, and then we're gonna go through some of the practice questions. So first of all, exam 2 started with chapter 2.9, which is linearization and linear approximation. So linear approximation is to kind of like, the purpose is to easily estimate, give me a second, to easily estimate the value of FB with B relatively close to A, but it's not a very like rounded or easily find value. So say thing like square root of 4.2. You know square root of 4, but we don't really know what is square root of 4.2. At that point, our function is going to be square root of x, and the value of x that we're trying to find is at x equal 4.2, and try to find what is fx at that point. And so we can use linear approximation. Basically, first of all, we're going to find what is the linear approximation of this function by using Lx is equal to fa plus f prime a multiply x minus a, with a is like the easily found value of that function. So say in case of 4 square root of x we're talking about, and it's x equal 4.2, a is going to be 4. So the value that easily found there, and then after that we're just going to plug in whatever value of x in to find what is L at that point. We also have the concept of differentials, which is kind of like similar to linear approximation. So I wouldn't really mention too much about it because it's kind of like just the same thing, just a different way so that you guys can represent the linear approximation. Then we have chapter 3, which is like the main part of exam 2, which started to deal with what's the derivative and critical numbers, the first derivative test and the second derivative test, what are their purpose and what do they tell us about the functions, and how do we use that to actually do curve sketching and just like sketch the graph out without like maybe a graphing calculator or something like that. So we have the concept of critical numbers. So a critical number in the domain C in the domain of F is defined as C so that you have f prime of C equal to 0 or f prime of C does not exist. So as I mentioned in this sections, to find all the critical number, there are two things you have to do. You have to find what is the general function of f prime of x and set that equal to 0 and find what value of x that is satisfying. Or you will set f prime of x does not exist. Especially when it's in the case of a rational function, then we can easily find where f prime of c does not exist when you have the denominator equal to 0. You also have the extreme value theorem. So basically, it's just a way to say, just like a way to assure the fact that you're gonna find an absolute maximum and an absolute minimum on some closed interval from A to B. If f is continuous on that, then you're definitely gonna have an absolute maximum and an absolute minimum at some number C and D in this interval. Also, to find the absolute maximum and minimum on an interval of a function, we can use the closed interval method. So basically what you do is that you make sure that you find the domain and you make sure that f is continuous in that on that given interval. Find all the critical numbers and the values of f at those critical numbers. Then you also find the values of f at the end point of that interval. And then you're just gonna take the largest as the maximum and the smallest as the absolute minimum. Next one, we have Rolle's theorem and mean value theorem. And as I mentioned in this section, the Rolle's theorem is just like a special case of the mean value theorem. So the Rolle's theorem have 3 conditions that you need to satisfy so that you can claim that conclusion. So f needs to be a function that satisfies continuous on an open interval, a closed interval, differentiable on an open interval, and the value of f at those 2 endpoints is equal to one another. So fa equal to fb on the interval from A to B. Then we conclude that there is a number c in that interval such that f prime of c is equal to 0. The mean value theorem is more general, where you don't have that third conditions that need the value at the two endpoints of the functions to be equal to one another. You only need f to be continuous on that closed interval from a to b, and differentiable on the open interval from a to b. Then you say there exists a number c in between such that f prime of c is equal to fb minus fa divided by b minus a. And so in the case of Rolle's theorem, when fa equal to fb, then f prime of c equal to 0. So that is the conclusion of the mean value theorem. Then we come to, I think it's 3.2 or 3.3, where we actually talk about what is the geometric meaning of the first derivative and actually apply it in graphing. So the increasing and decreasing test. So basically phi f prime of x, and on the interval the f prime of x is positive, then you have f is increasing on that interval, and if the f prime of x is negative on some interval, it's decreasing. Then you have the first derivative test, allowing you to say if the critical numbers that we found has a local maximum or minimum at that point or not, or you don't have any extreme values there at all. So you have a local max or a local min when f prime of x change size from either positive to negative or negative to positive, depending on the maximum or the minimum that you're looking for. And if f prime doesn't change sign at c, there's no local maximum or minimum at c. We also have a concavity test. So concavity test is concavity is like whether the function is concave up or concave down, like this. So you have, if you have a second derivative of f is positive, on the interval it's concave upward. So this one's concave upward and this one is concave downward when the second derivative of test is smaller than 0. The second derivative test also allows you to identify if it's a local maximum or local minimum at that critical number, but it's not very commonly used in this case, especially when you have the one that you can check for the change of signs of f prime of x, the first derivative. In this part, we also have like the change of sign of a second derivative where you have inflection points. So it doesn't really matter which sign is changing from, as long as it changed from either positive to negative or negative to positive of a second derivative, then you're gonna have an inflection points at that point. Then we come to 3.5, where we put everything together and we come up with a checklist for curve sketching. So as always, we need domain, intercept, x and y intercept. Symmetry, if you have f of x, you have to compare f of x to f of negative x. Do you have any asymptotes? So remember, to find a horizontal asymptote, you're going to take the limit of x approaching infinity and negative infinity. And then vertical asymptote, especially when you see the case of like a fraction, like a fraction or something related to like root, like square root, and you try to take the derivative of that, then try to see if you see like vertical asymptote is where you take the limit when x approach the values that the function is not defined. And then you have slant asymptote. This usually applies for fraction when you have the highest degree in the numerator is 1 power higher than the highest degree in the denominator. Then we also have interval of increasing and decreasing. As I say, we use increasing and decreasing test. Local maximum and local minimum, and then concavity and inflection points. As we mentioned last week, and we also go through the long division where you find the slant asymptote. When you have limit of x approaching infinity of fx minus a line with the equation mx minus mx plus b, and if that limit is approaching 0, where m is not different from 0, so it's a slide, it's a line with a slope, and it's not a horizontal line, then y equal mx plus b is the equation of the slant asymptote. And as I say, it's typical for rational function. Finally, we have 3.7, and it's kind of like just an extra sections, and I don't think it's gonna be like a main part of the exam. However, even though I didn't go over it last week, I put like some of the quick review here of the step that you need to do, say if you encounter like a word problem. So 3.7 is mostly about optimization. And so the step to do is first, main task is to find the function and the extreme values of that function. However, to translate from word problem to mathematical symbols, this is the step that you need to follow. So first, read the problem, and you have to be able to understand what the hell is going on there. Because if not, there's no way you can draw like a function and kind of like the relations that you're gonna take to find extreme values of that. So basically, you have to understand the problem and know what they're asking for. Draw a diagram. I would say I always do this because a picture's worth 1,000 words. It makes life so much easier, and it can make you visualize everything in a second. Try to put like, say if you, it wouldn't be something super crazy, but it should be something like volume, signs, and maybe like surface area, some things like that. Then it should be something really familiar with you. Either it's really related to math or just something in reality. So try to introduce the notation and the express the ask, and if given quantities in some of the symbols that are familiar to you, and you know like the correlations between those variables. And then yeah, when you assign them, kind of like you kind of have a general idea of what is the relationship between these quantities. Write the ask quantity as a function of one variable. So try to state the questions in a way that you know, like that you can apply your calculus knowledge into it. Like put it in a quantity that you know, like it's gonna relate it to whatever already given, and you know that you have to take derivative and you have enough numbers to plug in. Find its domain. And then find the absolute local maximum based on whatever quantity that they're asking you to. So first of all, let's do some practice question. Let's see how many we have. Give me a second. 1, 2, 3, 4, 5, 6, 7. Okay, cool. So we have 7. Shouldn't be too bad. Okay. The first one, let y equal fx be a differentiable function such that f0 equals 1 and f prime of 0 equal to negative a. Use a linear approximation or differentials to estimate f of 0.1. So as I say, the first step is to find what is the linear approximation of the function at a equal to 0. So you have Lx equal to fa plus f prime of a multiply x minus a. So you have fx is, so you have f of 0 is 1 plus negative 8 x minus 0, which is going to give us 1 minus ax. Therefore, if you started to plug 0.1 in, you have L of 0.1, which is going to be 1 minus 0.8, which is going to give you 0.2. So this kind of problem shouldn't be challenging to you because the step is there, and you basically just need to take derivative and plug in the quantities that are already given. So this is kind of like a way, I would say, the question that you should target to definitely get the points in the exam. Then we have find the critical numbers of this function in the interval from -3 to 10. So first of all, this is a cubic root. So you don't really need to care if the expression inside the root is positive or negative. We only need to care if you have an even root. So you have f of x. So now take the critical number. So two things to do. First is find f prime of x and set it equal to 0 and does not exist to solve a function. So it's 1/3 x squared minus 6x plus 5 to the negative 2/3 multiply 2x minus 6, which is going to give us 2x minus 3 divided by 3 x squared minus 6x plus 5 to the 2/3. Now we have this one, and now we're going to solve for it by setting this one equal to 0, and the other side is f prime of x does not exist. So it's equal to 0 when you have the denominator is different from 0, and the numerator is equal to 0. or we have x equal to 3, and we just need to plug in this to make sure that this one is satisfying. So you have 9 minus 18 plus 5 is different from 0, so this is correct. Now on the other side, we said f prime of x does not exist, which is where you have x squared minus 6x plus 5 equal to 0. Factor this one out, we have x minus 1 multiply x minus 5 equals 0. So we have either x equal to 1 or 5. And both of these, as we mentioned, is all included in this interval. So we're going to take both of them. So we have the conclusion is that all of the critical numbers are 3, 1, and 5. So here, if you want to take care of the domain here is R, or from negative infinity to positive infinity, because the cubic root is a cubic root, so it's always defined regardless of what values is inside the root. Now let's go to the next questions. For this function, find the absolute maximum and absolute minimum on the interval. And this is, we're going to use the only method we learn how to do and find the absolute maximum and minimum is the closed interval method. So that's what we're going to use. First of all, you look at this function. You have fx is equal to 4 minus x squared divided by x squared plus 8. This one is continuous on negative 1 or 2, or more specifically is continuous and defined everywhere because the denominator is always positive. You have x squared is bigger than or equal to 0, and then x squared plus 8 is definitely bigger or equal to 8, which is bigger than 0. Now we're gonna find all of the critical number because that's a step in the closed interval method where we find all of the critical numbers first and find the values at those critical numbers and also at the end point. So you have f prime of x is equal to x squared plus 8 squared, negative 2x multiply x squared plus 8 minus 4 minus x squared multiply 2x. So now we're gonna have negative 2x cubed, negative 16x, negative 8x plus 2x cubed divided by x squared plus 8 squared, which is going to give us negative 24x divided by x squared plus 8 squared. Now, to find all of the critical number, we either set f prime of x equal to 0 or does not exist. However, you have an always positive denominator. So f prime of x is always defined. So you only need to set f prime of x is equal to 0, which is going to give us x equals 0. And it's also included in this interval. So it's included in this interval. Now we only need to find a value at 0, f of 0, f of negative 1, and then f of 2. And trying to see which one is bigger is going to be the maximum, and which one is smaller is going to be the minimum. So at 0 it's going to be 4 over 8, which is half. At negative 1 it's going to be 3 over 9, which is third. Then you have 2 is going to be 0. So you have absolute maximum at x equal 2 and f prime of x equal to 0. And then absolute minimum, oh actually this one is minimum, not maximum. Absolute minimum. And this one, absolute maximum, is going to be at x equal to 0, fx is half on this interval. So this is my final answer. So there's really nothing very challenging in these practice problems. You should need to make sure that you follow the steps and know the procedures of how to do the problems. Then we have the next one. Suppose that fx is a differentiable function defined on from 1 to 5, such that f1 is equal to negative 2 and for any number in this interval. F prime of x is smaller than or equal to 5. What is the maximum possible value of f0? So when it comes to these, the first thing that comes to my mind, and from all the theorem that we've learned so far in Math 140, the only thing that actually applies for this is the mean value theorem. And so to use that, we have to first check the three conditions. So it's given that f is differentiable. on 1 to 5. And then we also have, because all of the differentiable function is also going to be continuous on that interval, so the second condition is also satisfied. So now we can use the mean value theorem. So mean value theorem applies. So then we have the conclusion of the mean value theorem was saying f prime of x is going to be you're gonna have a value of c that equal to fb minus fa divided by b minus a, which is in this case going to give us f of 5 minus f of 1, which is 2, negative of negative 2, which is plus 2, and then 5 minus 1 is 4. Now we have f prime of c as given is always more than or equal to 2. If you use this correlation, you can have f5 plus 2 smaller than or equal to 8, and then f of 5 is smaller than or equal to 6. So our conclusion is that the maximum value of f of 5 is going to be 6. So that is based on the conclusion of the mean value theorem. And remember, we have to check the conditions to make sure that this one applies first. In this case, it's open-ended practice questions, so you might not want to look at the multiple choice, but in the actual exam, there might be answer choices like mean value theorem doesn't apply, or this one cannot be found, or not enough information is given, those kind of stuff. And they can always be right, where that's why you have to check the conditions to use the mean value theorem. The next one is find equation for the slant asymptote. And so this one is similar to what we did last week when we used long division, because here you look at the fraction. The highest power in the numerator is 3, and the highest one in the denominator is 2. So we can use long division to find what is the slant asymptote. So we have x squared plus 3x minus 3. Just give me a second, I need to charge in the computer because it's running out of batteries. So in this case, let's do, here we have plus 0x, just to like fill out a space. So we're gonna have, we divided the highest term to the highest term. So 3x cubed divided by x squared, we have, it's going to be 3x. Then we multiply back and change the sign on the other side, which is going to give us negative 3x cubed. And then we continue to multiply with the rest. So you're gonna have negative 9x squared plus 9x, which is going to give us negative 10x squared plus 9x minus 2. And look at the highest power here, it's still equal to the highest power of x squared plus 3x minus 3. So you're going to continue to divide this by that. So you're going to have 10, negative 10, and then you multiply back and change sign on this thing. So what we have is that plus 10x squared plus 30x plus, and then you change here is negative 30, which is going to give us 39x minus 32. In this, using this long interval, long division, basically we rewrite 3x cubed minus x squared minus 2 as 3x minus 10 multiply x squared plus 3x minus 3 plus 39x minus 32. And so if we take the limit of x approaching infinity, fx minus 3x minus 10, remember, we take the result here, not on this side. We're going to have limit of x approaching infinity of just this part, because this part is already minus out. So we have this divided by x squared minus plus 3x minus 3. And here you can see like the highest power here and there are different. And the denominator is going to approach infinity faster than the numerator. Therefore, you have a small number divided by a very big number, what you end up having as x approaching infinity, which is the limit is going to be 0. And so our conclusion is that the slant asymptote in this case is y equal to 3x minus 10, which is also the result of this division. Again, if you feel like you don't understand how I do this long division, feel free to email me and we can always schedule, like try to make this thing clear before you take the exam. Other than that, I'll go to the next questions. I think we have 2 more. Oh, this is actually, oh yeah, we have to have 1 more. And but the last one is like an optional one because it's section 3.7. So for this function, whose the derivative is graphed below. Okay, this is the graph of the derivative. This is a very important thing. Please read the questions before you do before you try to approach it in the exam. Because most of the time we think, okay, this is a graph, like everything is easy, I'll get this point. But in the end, we realize the fact that this is a tricky part because they don't give you the graph of your function, but they give you the graph of the derivative. So here, this is the graph of f prime of x. What can we conclude about fx? So from f prime of x, let's see what we can have here. Here we have is positive, negative, negative, and then slightly positive here, and then negative again. We can conclude that we have a local maximum based on the first derivative test and a local minimum. So when you go from negative to positive, it's decreasing and then increasing. So decreasing and increasing. It's going to be a local maximum at x equal 0. Then you have again negative to positive. I guess it's gonna be like 5.5. And then you have local maximum at x equal from positive to negative. So you go positive to negative. So it increase and then decrease. So that's going to be a maximum, which is here at 1, at 6, and that's it. Now let's see if we can conclude anything about concavity and inflection points. Now look at it here, where you have the slope of f prime of x is going to be slope of the graph of f prime of x is going to be f double prime of x. So now let's see where the slope change signs, and that should be pretty clear, where you have is going up and going down. So we have is going up here, and then you have the slope going down here. So slope is positive here and change to negative, and the change at this point. So we can say, I would guess that's around half. So we have inflection points and concavity. So inflection point at x equal maybe half at this one, and also the same here, it go down and it go up. So it changes sign here. I would say is equal to 3. And again, it's go up and go down, and it's gonna be, I guess, it's around this 5. Oh, it's around 5.8, and so on. So that is concavity, where you have the second derivative, which is the slope of f prime of x, change their sign. Now let's see which part is concave upward. So the slope of that is going up here. So this is a positive f double prime of x, which is going to give it maybe I would write down here. So from here to here, it is concave upward. So now the slope is going down. So here to here is concave downward, up again. This one concave upward, and then from here is concave downward because the slope is negative. And so that's everything that we can conclude in this questions based on the graph of f prime of x. So again, I would highly recommend try this one. It can be a little bit tricky if you like approach it for the first time, but if you have done your practice and get used to it, I think it's a really good way to see if you actually master the knowledge or not. And then finally, we have practice questions for 3.7. So this one is pretty similar. So we have a water tank has the shape of a point down circular cone. So this is the circular cone. As I say, always draw a diagram. So you can either choose to read the problems and make sense out of yourself, or you can read and try to like draw diagrams at the same time, because essentially you have to draw diagrams and it's really hard to remember the entire paragraph. and you have to like read it again sentence by sentence and draw a diagram. So I just like do 2 steps in one. With a base radius of 4 meters, so a radius, so put this one, and this part is 4 meters, and height is 6 meters. Now, if water is being pumped into the tank at a rate of V equal dV over dt, so dV over dt equal 16 cubic meter per minute. Find the rate at which your water level is rising. So you pump it in, and this is the water, and this is going up to this. So it's asking what is the rate of, so dH over dt when you have the water is 3 meters deep. Now, let's see how we're going to relate. So first of all, what is the volume, the relation between volume and radius? So you have volume is pi r square h in this case, and it's 1/3. So this is the formula for the volume of the circular cone. And so they give you dV over dt and then h, and they ask you to find what is dH over dt. Now we have to put all these in one variable first, because we only need to find dH over dt, but we have no idea about r. However, let's see what other thing that we haven't used, which is the 4 meter and 6 meter. So the thing that we need to know about cone, circular cone, is that when you pour water in, the rate of change of the radius, so like the radius at any point is going to have the same proportion, the same ratio with the height. Like say you have this and this, so the ratio here, the radius here and the height here is still, you still have the ratio of 2/3, which is the ratio of the tank, of the original dimensions of the tank, which is 4/6, which is 2/3. Now we can now put V into just one variable, which is pi/3, multiply 2/3 of h square multiply h, and it's gonna give us, sorry, not there yet, 4/27 pi h cubed. Now let's take derivative. So you have, with respect to time, dV over dt is going to equal 4/27 multiply pi multiply 3h squared, which is going to give us 4/9 pi, multiply dH over dt as well. So pi h cubed h squared multiply dH over dt. Now we can just plug in the values that were given and we solve the problem. So we have 16 equal to 4/9 pi. H is 9 dH over dt. Therefore, you have dH over dt is going to be 4/pi. And that is also my final answer, and then meter per minute. And also my final answer for this question. So as I say, the challenging part is to be able to represent, draw diagrams, see the relations, and also this is the tricky part where you have to actually understand the problem, where what is the rate of change in the circular cone, and see what are the numbers that you haven't used. That can give you some key insights about how to solve the problem, just like in this case. And the rest is just plug in, take derivative, and all that. So with all that in mind, if you are afraid that you might be confused and get, freak out when you see this word problem in the exam, because I haven't really looked at your exam, and there still can be a chance that you can have like a small problem about this 3.7 sections. These are the practice problems that I recommend trying in the book. You might find them challenging, but at the same time, please feel free to email me to ask this weekend, and especially give me at least 24 hours before your exam so that I can give you, I can answer your email to the best of my ability. Other than that, good luck in your exam, and I'll see you guys next week. Have a great weekend and a wonderful exam week. Thank you.